Hey everyone, my name is Nitin Kohli. I'm a postdoc at UC Berkeley, and I'm here to talk about how we can create differential privacy guarantees for statistical analyses that we consider as black box code. And I want to just point out that this is joint work with Professor Paul Iskowski as well. And before I even start the talk, I want to keep the talk very casual today, so you're not going to see a bunch of math equations on the board. You're going to mostly see a lot of pictures, and I want to talk about the intuition of how we developed our solution. But that being said, during the Q&A or afterwards, if you want to ask me or Paul any more technical questions or any questions about related work, please feel free to do so. That being said, let's go to Fantasyland and think about the following interaction. So Paul and I, when we started this project, were considering an interaction between a data holder and a researcher. Our goal throughout this project was to enable data access to researchers who want to run new scripts on data for scientific purposes, for humanitarian aid purposes, basically a wide gamut of analyses. Now, we're in this room because we care about privacy, and we know that sometimes researchers, even if they're acting in the best intentions, can accidentally learn about individuals and data sets. But even more so, researchers don't always have to be very benevolent. They can actually be adversarial. So what Paul and I are considering is how can we provide privacy guarantees even in the face of an adversarial researcher? So in this case, what I want us to do is pretend that we're an adversarial researcher right now, and we want to learn something about our session chair, Aaron, who is probably in this data set D that the data holder is quite literally holding here. If I wanted to learn, for example, like what Aaron's income is in an income data set, for example, one thing I might try to do if I'm a sneaky researcher is I might actually try to just output the average of the data set, the average income in there. But what I'll do is I'll hide Aaron's income in some trailing digits far down past the decimal point to kind of at least make it look like I didn't do anything sneaky. Another thing I can do is, let's say I just want to figure out if Aaron was in the data set or not. One thing I might do is, once again, just hide a bit of 0 or 1 somewhere in a decimal point far down of a legitimate looking query. That way, when I, the adversarial, look at it, I can kind of just take a peek and see his presence or absence. Alternatively, we know that adversaries can also be very creative by just writing their code to conceal their strategies. In fact, many of us who have ever taught like introductory programming, data structures, and algorithms have seen some obfuscated code from our students of their own, typically not on purpose, but just by default. And adversaries can also do very creative things as well to hide their intentions. So what we want to do in this project is consider a way to still enable access to data sets for statistical analyses, even in the place of arbitrary code. And before I go on, I want to explain what some of this funny notation is up here. So we're going to say a data holder has a data set D in some data universe D star. And the researcher has a script, which we'll call R for the researcher script. It computes over the data set and can output K real numbers, or we have this special symbol here that stands for non-response. And what we want to do is construct a way to mediate this interaction between the data holder and the researcher automatically. And one way we're going to do so is with what we call a privacy wrapper. So a privacy wrapper you can think of as akin to a function wrapper. It's a way to mediate this interaction between the data holder and the researcher. So on our screen here, we have this notation with W. So mathematically, a privacy wrapper is just a function. It takes two inputs, a data set and a researcher script. And what it tries to do is return a noisy output over the space that the researcher script ran over, and possibly don't respond if the script can't be executed safely. And while this is like the picture I want us to keep in our mind for the next 8-9 minutes, we need to actually write down what we formally mean by privacy here, because we have a privacy wrapper and a private answer. Our work is highly motivated by differential privacy. So what we'll say is that a privacy wrapper imposes differential privacy if, once we fix the researcher script R, W of R behaves differentially privately as normal. So in other words, we have our wrapper already set, and once we get a researcher script, we can get an output that satisfies differential privacy. This is actually quite different than what many folks do in like global sensitivity, where I know I want to compute a proportion query first, and then I find the sensitivity and then compute. We're saying here, you can give us an arbitrary statistical script R, and our goal is to give you a private answer afterwards. So we're in a more general space here. Great. And kind of like the definition of differential privacy, where it really doesn't tell you exactly how to create algorithms necessarily. Nothing about our privacy wrapper here tells us how we should go about doing so. So what I want to do is present our privacy wrapper that we put in our paper and just talk about the intuition for the two building blocks we had in there. So our first building block is the idea that we want to look at a data set, and if we want to compute a differential private answer over it, let's try to find parts of the data that are quote-unquote favorable for privacy. And since we have differential privacy in mind, what we want to do is we want to look for subsets of the data such that when I compute over them, if I remove individuals, the answer on the researcher script really doesn't change by too much. Because in that case, we already know if I add a little bit of Laplace noise, we're likely to get something that satisfies differential privacy. So let's actually get slightly more formal here. So we say a subset is stable with these 4 funny parameters here if, when I further subset that subset, the researcher script on that subset A and B are still close with one another, where close is technically defined as being within some L1 norm of each other. And just kind of teasing ahead why this is helpful is the L1 norm is very nicely related to Laplace noise. So this gives us kind of a duality to then talk about privacy protection versus just outputs in the space. Cool. So one might hope that, oh, hello, stereo. One might hope that the idea 1 is just sufficient to get differential privacy, but it actually turns out something weird happens. And since we look for subsets that have favorable privacy properties, it turns out that the existence of these favorable privacy properties can leak information about the data set. For those of you who are interested, ask me about it during the Q&A. I have an attack on this that I think might be interesting for folks. So what we have to do to stop this attack is actually add a little bit of noise to the size of the subsets we look at. So what we want to do is we want to construct a distribution to help us pick the random size of the subsets we're going to look at, check if any stable subsets exist, so that way we can get favorable sets for differential privacy to just add a little bit of Laplace noise and get a private answer if we can. So here's our algorithm. We called it Tahoe. It stands for trim and withhold or execute. And I'm going to just give the overview of the algorithm. If you really want to see it, you can read the paper. You're all adults. So our data holder has 3 inputs that it gives. The data set D, the classic differential privacy parameters epsilon and delta, and this parameter alpha that's related to stability. Whereas the researcher, all she has to give us is a researcher script R and a noise scale for the type of noise she'd like to see at the end, which can be computed based off of her tolerance for error. And at a high level, our algorithm functions as follows. All we're going to do is sample the size of the stable subsets we want to consider from a distribution G. And just so you know, in the paper, G depends on epsilon, delta, and alpha, and we rig it to give us great privacy properties. And what we'll do then is going to seem kind of nuts, but it actually works out well. We're going to compute the set of all stable subsets of size n. So if I imagine I have a data set of size big N, and I look at the subset graphs of size little n, I'm going to look at that entire row of the subset graph and try to compute which of those subsets are stable. This might seem computationally inefficient, but there are recursive ways to actually formulate this, and in special cases, it can be computed quite quickly. If we can find a stable subset, life is good, but if we can't, we're in trouble. So if we can't find a stable subset, we just won't respond. And the way we rig the distribution G, there's no extra privacy loss from that. Otherwise, if I can find a subset that's good for differential privacy, I'll simply compute the researcher script on it, add some Laplace noise, and output that. So this is why it's called Tahoe. I trim the data by sampling some n from a distribution, and what I'll do is I'll withhold from reporting an answer if I can't find a stable subset. Otherwise, I'll execute the script with random noise. Cool. So there are a lot of results in the paper. Here's just 3 of them as an advertisement. The first is we can actually prove that Tahoe imposes epsilon delta differential privacy for any script R you give us. That's really cool. Secondly, in addition to privacy, we have some really neat accuracy guarantees when our scripts behave like classic statistical estimators. So if I have a script R that's an unbiased estimator or a consistent estimator from classic statistics, and Tahoe is rigged to never output non-response, then Tahoe will still preserve the unbiasedness or consistentness of the original script. So for statistical tasks, we're not actually becoming more biased or losing consistency along the way. And lastly, Tahoe runs rather nicely, assuming the data alphabet is of finite size, and the original script won't take forever to run either. At an intuitive level, when we look at this big O notation here, you might notice that it just contains the size of the data alphabet and not really the size of the data. And that's because when we have a data alphabet that's finite, we can write it as a histogram notation using the classic Dwork and Roth techniques from algorithmic foundations. And presto bingo, the runtime is quicker. So in conclusion, right, if we want to actually create a privacy wrapper that can work for arbitrary statistical analyses, we have to be careful because adversaries can be really creative and really sneaky. And our privacy wrapper imposes differential privacy, has strong accuracy when we talk about statistical scripts, and can run efficiently when our data alphabet's small, kind of medium, but definitely finite. And one thing I know we're excited about is improving access to data sets that don't have access to them already for privacy reasons. And we think privacy wrappers and other arbitrary code systems are a way to do that in the future, and we hope other folks think so as well. Thanks.
All right, thanks, Nitin. I'm looking for questions in Zulip, and I'm not seeing any.
You know the time back.
But I did want to ask about the runtime. I know you have this theoretical guarantee, but in practice, some of these, even simple statistical estimators can be kind of time intensive. Mm-hmm. So have you run these on anything of any complexity, and do you know how long it actually takes?
Yeah, so let me actually, I had some appendix slides in case folks wanted more details. So So yeah, for example, if we consider the task of let's just say we're computing a normalized histogram, for example, so just like a multidimensional proportion query, we actually found out that we can run this quite efficiently just on my single laptop here. I haven't ran it for anything more complicated that you might see in an intro theoretical stats course in the graduate course yet, but we're hoping that future research can test out more ways to optimize this runtime.
We still have time for questions, so if you have any questions, put them in the Zulip chat while the next speaker sets up. All right, if not, let's thank our speaker again.